we are going to start the lecture on advanced reaction engineering. So, in that lectures we will discuss about the pressure drop for a packed bed reactor. So, already we have discussed on this particular reactor. So, how the if we charge the catalyst inside of the reactors in a packed bed reactor, how the pressure drop will vary, at the same time the conversions will vary, that we have discussed. So, today we will just one numerical problem or examples that we will discuss. So, where how to calculate the pressure drop for a particular reactors, or pressure gradually changes along the length of the reactors or by increasing the weight of the catalyst. So, that we will discuss. Okay. So, means here the examples will discuss about the oxidation reactions. Okay. So, in these reactions here you can see. So, that example we have taken ethylene glycol. So, that is the oxidation reactions or ODH reactions you can say. So, ethylene so ethylene production. So, from ethane to ethylene productions, that is ODH reactions, and after that the product ethylene will form. So, that will be converted into ethylene glycols. Okay. So, this is the ethylene glycols and this is the ethylene. So, ethylene will be partially oxidized in presence of oxygen or air, in presence of catalyst. At temperatures we have to maintain high temperature and high pressure, that may be 260 degrees centigrade, and pressure that may be 10 bar 20 bars we can use for this particular reactions using silver catalyst. So, this catalyst has industrial importance. So, already have discussed. So, it has many industrial importance, means polyester formations, antifreeze, surfactants, as well as solvent. As a solvent it is used. So, when a packed bed reactors, here is the packed bed reactor. So, it would be taken for this particular conversions or ethylene to ethylene glycol productions. So, at the bottom of the reactor, so we have to charge ethylene and oxygen, and then from the top of the reactors we are getting ethylene glycol. So, here we are putting catalyst, that is in the form of bed of catalyst bed, that is W amount of the catalyst we are charging. So, here we have to find out the amount of the catalyst is required for a desired conversions, that may be 60% conversions if you want to achieve, let us say. So, then how much amount of the catalyst we have to placed in this reactor. So, here oxygen we are taking, but pure oxygen will not take for that as a reactant. So, the ethylene. So, here ERs we have to use. So, with ethylene that will be passed, and that oxygens remain inside of the reactors that which passing or entering with the air. So, that would be react with the ethylenes, form ethylene glycols. Okay. So, here few informations for these reactions is given. So, here let us say the temperature of the bed temperature or reaction temperature is given, pressure is given, and that is 10 at atm, and here the cross sections area AC, that is the here's inside of the catalyst bed. So, that small tubes are there, inside of that tubes catalyst particle will be charged or placed, and then so that would be arranged inside of the beds as if it can uniformly means distributed inside of that particular reactor. So, here's 10 tube banks like that was there, and that diameter of each bank is 1.5 inch. Okay. And it is 40 scheduled tubes packed with catalyst, and 100 tubes per bank. There are total 10 banks of tubes are there, and total each banks 100 tubes are there. So, total 100 into 10. So, 1000 tubes are there inside of the reactor. So, that is filled up with the catalyst. So, then other information is given, that is the molar flow rates of that component A. Let us say ethylene is given, that is molar flow rate is per tubes, each tubes. There are total 1000 tubes are there inside of the reactors, and for each tubes the amount of the molar flow rates of that ethylene is 3 into 10 to the minus 4 pound mole per second is given. And so, here's the density of this particular catalyst density, that is given 120 pound mole per feet cube. Okay. So, and catalyst particle diameter is also given, that is 1/4 inch, and the void volume or void fractions, that is given 0.45 for this particular when catalyst is placed inside of the reactor. So, then void fraction is importance phi, that is equal to 0.45, that is given, and here's rate law for this particular reactions from the experimental data or lab scale data, that is given here, that is the rate equations minus R A prime equals to K rate constant P A partial pressure of component A, that if you consider ethylene, that is the A, and oxygen if we consider B. So, then partial pressure of component A and B is given P A, P B, P A to the power 1/3 and P B to the power 2/3, that is the rate law, and here rate constant is given for this particular reactions at 260 degree centigrade. Since the reactions will conduct at 260 degree centigrade, then the reaction rate constant that is required for 260 degree centigrade. If we conduct it is at different temperature, the rate constant also we have to accordingly we have to choose the different rate constant reactions. So, let us say if it is 300 degree centigrade, then accordingly rate constant also would be for that particular temperature. So, these are the information is given. Now, ethylene feed rate is given here, ethylene feed rate 0.3 pound mole per tubes I said. So, how this has been calculated. So, here let us say 0.3 pound moles per second, that is the total feed rate. If there are total 1000 tubes are there, for each tubes that pound moles would be fed or pass through that individual tubes. So, if we convert that into pound moles per hour, so then it would come this. Okay. So, then ethylene feed rate for each tubes is given. So, now the step by steps we will discuss, means how to calculate the total weight, the amount of the catalyst is required, and from the beginnings we said that we need 60% conversions. Okay. X equals to 60%, that is the fixed, and for that how much amount of the catalyst we required if there is reactions and at the same time pressure drop is there. So, step 1 is the mole balance, that mole balance equations already we have discussed for the packed bed reactor, the that is the differential mole balance equations or design equation that we know. In the step 2 is the rate law, rate equations. So, rate equation that is also given. So, here rate constant is also given. So, here it is given P A and P B, that is the partial pressure of component ethylene and oxygen is given in terms of partial pressure. So, we will convert that into in terms of concentrations. Okay. So, then concentration and partial pressure, how they are expressing this, C equals to P A by R T. So, we are substituting that P A in terms of concentration and R and T. Okay. So, then it is coming this. Okay. So, then rate we are expressing in terms of concentration. Now, individual concentrations we know. So, then in the step 3 we are considering or assuming that reactions is considering an isothermal temperature, means the temperature throughout the bed remain the same or constant at 260 degree centigrade we are maintaining, and then volumetric flow rate as a function of pressure, that also we have discussed in our previous class. So, here if we want to concentration, we want to express in terms of conversions and pressure, then we have to substitute this here, and then after rearranging or simplifying, so we can get this. So, this is the concentration C A component A, that is the ethylene, and initial concentrations, that is the 1 minus x, that is the conversions, and y is the pressure ratio, that is here, and this is the volume fractions here epsilon and 1 plus E x is there. So, then this is for concentration of component A, and similarly for component B also we can write this. Okay. So, that also we have discussed in your previous class. So, therefore, I am not going to details discuss on this. So, after that if we simplify these equations, then concentration of C B would come, and this is in terms of initial concentrations and 1 minus x, y is the pressure ratio by 1 plus epsilon x. So, we know concentration in terms of conversions and pressure. Okay. So, now these two we can substitute in the these rate equations. Okay. These concentrations we can substitute in these rate equations. Okay. So, now in the see we have this design equations, we have these rate equations, and we have this concentration in terms of conversions we are substituting here. Okay. So, once we substituting here, so these rate equations see, so it would be simplify and we will get this. Okay. So, if you simplify this, so first you have to substitute C A and C B here, C A and C B here, and then if you rearrange these equations, so then rate will come K R T naught C A naught half to the power 2/3 1 minus x y by 1 plus E x. So, here's these terms we are considering as a k prime. So, here we have written this is as a k prime equals to just for simplification this equation or final design equation. So, k prime equals to k into P A naught into 1 by 2 to the power 2/3. So, that we can write it here. Okay. So, then finally, minus R A prime, that is the rate for this particular reaction is this is coming. Okay. So, now this we can this rate we can substitute in this equation, this is the design equation. Here we can substitute this rate in terms of concentrations, initial concentrations, conversions and pressure ratio. So, this is the design equations. So, design equations we are substituting this rate part here and then dx by dw that we are getting is this is the equation 1. Okay. So, now the differential form of argon equations that also we have discussed, that is the differential form of argon equations is dy by dw minus alpha 2 y 1 plus epsilon x into T by T naught, that is the differential form of argon equations where the pressure, how weight of the catalyst is related, that detail of these derivations we have discussed in our previous class. Here directly we are using these equations. Here we assume that the reactions will occur inside of the reactor at isothermal conditions, then T equals to T naught and this part we can eliminate. So, then by this way we will get this dy by dw equals to minus alpha by 2 y into 1 plus E x. So, now we have equation 1 and equation 2 for this particular reactions. Okay. So, now here's molar flow rates F A naught or epsilon value, alpha value, these are the components we have to know or we have to find for this particular reactions. Okay. So, how this value is coming, so that we will discuss. Okay. Alpha and beta 0 value also we have to calculate in the step 6 how we will proceed. Okay. So, this is our reactions I said. So, this is component A and half component B, we are giving component C, that is the product. Okay. So, that is we are expressing in terms of A, B and C. So, here I said that pure oxygen is not passing. So, instead of that we are means charging ERs, that with ERs nitrogen also is there as a inert component that will be passed through that reactor. Therefore, so that component mole also we have to consider for the total mole fractions of individual component or total molar feed rate of total system reactant that is passing or entering inside of the reactors. For that we have to include that part. So, here the molar feed rate of ethylenes that is the reactant A, that is given F A naught, that is initial, that we have discussed that calculations in the previous slides. So, F A naught equals to, it is given 1.08 pound mole per hour. So, here this rate equation is given, K is given rate constant, density of that catalyst if it is given or it is also given for this particular problem, rho C equals to 120 pound mole per feet cube, and this is also the Voigt fraction is for this particular system is given. So, here moles of individual component, here 3 components are there. So, component reactant 2 and one inert component is there. So, first ethylenes molar flow rates is given 3 into 10 to the minus 4 pound mole per second or 1.08 pound mole per hour. Similarly, for oxygen also molar feed rates if we express in terms of F B naught, that is equals to that would be half of ethylenes from the stoichiometry you can say. So, it would be half of ethylenes. Okay. So, then from here it is coming 0.54 pound moles per hour. Okay. So, that oxygens will be required 0.5 pound mole per hour. Similarly, for inert component that is the nitrogen. So, that molar flow rates remain constant initially and finally, but that also we have to calculate for to get the total molar feed in from the inlet of the reactor. So, that would be 1.5 into 10 to the minus 4 pound moles per second multiplied with this and divided by this. Okay. So, then from here we are getting 0.203 pound mole per hours, that is the nitrogen entering so with the reactants. Okay. So, then total molar flow rates that we can sum up of this, then total molar flow rate that is due to the component A, that is ethylenes. for component B, that is the oxygen, and that is nitrogen for component nitrogen, inert component. So, total molar flow rates is coming this. So, from here if we know ethylene molar flow rate is this and total molar flow rate is this, from here individual component mole fractions we can find out. Okay. So, mole fractions, so why not, that is the mole fractions of ethylenes in the reactors, that is 0.3. How that is coming? So, Fa naught we know, Ft naught that we have just calculated. So, if we divided that, then that would give mole fractions of component A in the systems. Okay. So, similarly that is the changes of the moles from the stoichiometry we can say here is 1, this is half, this is 1. Okay. So, the changes is this, the changes of the moles, that is the delta equals to per unit moles of A. So, equals to delta equals to minus 0.5 is coming. Okay. So, then epsilons that is the fractional changes of volumes during reactions, that we can write y a naught into delta, that would be epsilons. Okay. Epsilon equals to y a naught we know, and delta value is this. So, then epsilon value is coming this, okay, for this particular reactions. So, now the partial pressure of component A, that is the ethylenes mole fraction into total pressure. Mole fraction is this that we have calculated, and total pressure of the system is 10 bar or 10 at atm. So, then partial pressure would be 3 atm. Okay. Now, from here we can find out K prime value, K prime equals to K into P naught half to the power 2/3, that is already we have means discussed when we derive the this part, we already have considered this K prime, that is the constant. So, how that part we can calculate. So, here's K that is given, P a naught that we have calculated, that is the partial pressure of component A, that is ethylene, and so by that way K prime value, numerical value we can find out. So, K primes we know, epsilon value we know. Okay. So, now we have to calculate alpha and beta 0 value, okay, alpha or beta 0 value. So, here this type of equations or the relationship we have derived in our previous class, alpha equals to 2 beta 0 by AC rho c 1 minus phi p 0. Okay. So, AC is the cross sections area for the tube, individual tube, so that is given. So, here's cross section area of reactor, sorry. So, that is given. AC we know, density of the catalyst particles, that is also given. So, 120 pound mass per feet cube, and so phi is also given, and P 0 is the total pressure of the system, so that we know. So, then from here these are the component knowns, but only beta 0 value is unknown. So, beta 0 value if we know, then alpha value we can calculate. So, beta 0 that is the pressure parameters, pressure drop parameter for packed bed reactors. From the argon equations we have considered this is the constant, beta 0 value is this. So, here's almost all components in this particular beta 0 is given. So, here's g is the superficial mass velocity that you have to calculate, that is equals to mass rate per unit cross section per unit area. Okay. So, that you have to find out. So, except that viscosity here, so that is the gas, here we consider that air as a gas that is passing that has a temperature to 60 degree centigrade, and at 10 bar that is or 10 atms that is entering. So, here viscosity of that airs at this particular temperature pressures that you have to collect or that is given for this problem, and rho 0 that is the density of air that is given, and particle diameter, here is the dp is the particle diameter. So, diameter is 1 by 4 inch, that is also given in this particular problem, means catalyst that we have taken, it has a particular dimension, that is the 1 by 4 inch particle, each particles catalyst particle, spherical particle. So, that diameter is in terms of feet is this. So, diameter is given, and Gc that is the conversion factor that is given for this particular system. So, then so rho 0 value is given, Gc is given, dp is given, phi is given, and viscosity of that gas is given. Only the superficial mass velocity g value we have to calculate, and for that mass rate we have to know. If we know mass rate and cross sections area that is given, so we can put then g value we can substitute here. So, then mass rate how to find out the mass rate m dot, or we can say that this is that amount of pound mass per hour of that reactant that is passing inside of the reactors, that we have to calculate. So, individual component mole molar flow rate that is given for, or we have calculated for based on the stoichiometry. So, here molar flow rates of feed components. Okay. So, that was A, B and I. So, that is in terms mole per hour is given, individual component molecular if you know, then if we multiply it with the molar flow rates, see here mass rate of ethylene, that is we are getting molar flow rate multiplied with molecular rates, then pound mass per hours we are getting for ethylene. Similarly, for oxygens the mass rate, that is we are getting 0.54, that is given molar flow rate multiplied with the molecular rate molar mass. So, then mass rates for component oxygens we know, mass rate for nitrogen also similarly we can calculate. So, that is given, and this total molecular weight of this we know. So, then here's individual component mass rate. So, it was mole per hour, we are converted into mass per hours we are getting. Okay. So, for 3 components. So, then total mass rate for that component AMT 0, that is total mass rate equals to, we are adding up summing up this and this for 3 components. So, then it would give 104.4 pound mass per hour, that feed is entering through that reactors at the bottom. Okay. So, if means from here we know the total mass rate that is entering for that particular reactions. So, then superficial mass velocity we can calculate. So, superficial mass velocity how to calculate? So, I said AMT 0 by AC cross section area if no. So, AMT 0 we have calculated or measured, and then cross section area we know. So, then superficial mass velocity for this particular system we know. So, then this pressure drop parameter beta 0 is this. So, here if we substitute all components, so then beta 0 the pressure drop parameters will get. So, here all component we are substituting, or we are numerical value we are putting it here, and then beta 0 value will get. So, beta 0 is coming pound feet per feet cube, we can convert that into ATM per feet, means beta 0 I said it is pressure drop parameters, pressure drop per unit feet, means if it is the reactors actually here. So, if total length may be any means this is the length. So, here let us say this is the P 0 to P. So, here means initially here it was let us say 10 bar 10 atm pressure. So, this is the inlet, this is the outlet. So, here per unit length beta 0 actually indicate the pressure drop in along the per unit length of the bed or the reactor. So, therefore beta 0 unit is atm per feet. Okay. Means pressure drop changes per feet or per unit length of the reactor. So, beta 0 value we have measured or we have calculated for this particular system. So, once we know beta 0, then we can calculate alpha value. Okay. So, next in this type of correlations we have discussed in your previous class. So, therefore, the pressure drop parameters we have measured 0.0775 atm per feet, that we are substituting here, and AC that is the cross section area for the systems we know, density of the catalyst we know that is given, and phi is the void volume or void fractions that is given 0.45, and P 0 is the total pressure of the system, that is the 10 atm that was taken for this particular reaction. So, once we put all these components then we will get alpha value. Okay. So, here next we will go to the summary, means whatever we have done the calculations. So, then we have to means solve by means individual components, that is the known component for this particular system. So, that first we will evaluate based on the data or information is given. Once it is given, then the differential equations we can solve easily. Okay. That would help us to simplify the equations and to easily we can means error free calculations, or we can get the solutions. Okay. So, these are the two equations already I have discussed. So, these are the two equations, one is the from the design equation and one from the argon equations we have derived. So, here if you look into this particular equations, here in the first equation is k prime is there that we have measured or we have calculated, that is yes this is the k prime. So, k prime value we have yes here we have calculated based on all parameters are given, k is given, P naught is given. So, K prime is given. So, K prime is calculated. Okay. So, we can provide K prime value, and here F A naught, that is the molar feed rate of component A, that is the ethylene, that is given or that we have, that is known. So, this K prime is known, F A naught is known, E is known, fraction volume change also we have calculated or we have measured. So, that is minus 0.15. Okay. So, here's this value K prime is known, molar feed rate of ethylene, that is the known, F A naught is this. Okay. So, these are the components, means in the equation 1 is known, only unknown is x and y, that is the pressure changes or pressure ratio, that is the unknowns with dx by dw. Okay. In the second equation also similarly, in the second equation alpha value, that is we have measured, that we can put it here, and epsilon value, that is the known. Okay. Alpha value is known and epsilon value is known. So, we can put these are the, we can provide or we can supply for this solution of these equations. So, then only unknown is for this equation is also x and y, that is the P by P naught. Okay. So, these are the two components are unknowns in the right hand side, and left hand side is dx by dw and dy by dw. So, now this is the two differential equations are there. So, these two equations you have to solve by using ordinary differential equations, polymath or other type of MATLAB you can use. So, in the differential equations just you have to put these two equations, and these are the known parameters you have to put. Okay. Known parameters whatever we have measured, so that you have to put. Okay. So, we have to put, and then right hand side all the known components we know. So, now initial guess some things we have to put for to run that program. So, here boundary conditions, let us say W equals to 0 initially, when x equal to 0 means when there is no catalyst, then conversion is 0, and so then y equals to, and at that times pressure ratio, that is equals to 1, y equals to P by P naught, that is P equals to P naught by P, that is equals to 1 at the beginning. Okay. When just started reactions or at the entrance of the reactors at the beginning. So, that is the one boundary conditions, and at that conditions since we are going to get 60% conversion. So, therefore, we assume that at the beginning that 60 pound mass of the catalyst that was taken to run that program. So, initial guess that we have to put it there in that program. Okay. So, then once you put that, so then that we will get that some solutions or output from that ordinary solver or after solving these two equations. Okay. So, here graphically means the output would comes y axis x and y is there, and x axis is w, means x axis weight of the catalyst, that is gradually increasing, and y axis, that is x and y, that is up to 1. Okay. So, from here you can see means that output or the result is coming, if we plot it graphically, means after solving that equations we get W x y, that is the pressure ratio, these are the value will come. So, from here 0 to up to 60 kg of the catalyst that we have taken, let us say for assumption. So, here this value will come, and corresponding the conversions value also will come from the output of that equation, two equations, and then corresponding pressure drop also will come. So, if we plot them, so then it would be nature would be conversions along the increasing of the catalyst. So, from 0 weight catalyst, 0 the weight of the catalyst, that is at the beginning it was 0, from here conversion was low, and then if we increase the catalyst weights inside of the bed, the conversion gradually will increase, the nature should be like this. Okay. So, similarly, the pressure, how they are dropping the pressure inside of the bed. So, initially the P by P naught, that was 1, it was started when there was no pressure drops, and then it going down. Okay. See here at the beginning when there was no catalyst, or at the starting point of the reactor, it was the pressure ratio, that was 1, P by P naught equals to 1. Okay. Then gradually increasing of the catalyst. So, the pressure that is gradually changing like this. So, let us say if we put that amount of the catalyst, so then corresponding conversions and pressure at that particular point. So, we can easily means find out or we can say that. So, when 10 kg of the catalyst or 10 pound mass of the catalyst was placed inside of the bed, on that times the conversion should be this and pressure at that particular point should be this. Okay. For due to that amount of the catalyst once we charge, then the pressures that will vary this way. Okay. So, similarly, if we charge more amount of the catalyst, so then conversions is that and pressure drop also corresponding pressure drop is this. Okay. So, these are the value we can find out. So, okay. So, conversions. Similarly, the when reactant is passing inside of the reactors, volumetric flow rate also will change with the pressures changes, conversion changes, volumetric of the total reactants that will changes. Means here's volumetric flow rate, how they are related, V equals to V naught into 1 plus C x P naught by P, T naught by T. So, if we consider T equals to T naught, so then isothermal condition this part we can eliminate, and then this P by P naught that is equals to Y. So, we are substituting it here, and these equations we can express F equals to volumetric flow rate ratio V by V naught. V naught is the initial volumetric flow rates and V is the inside of the bed at any location. So, we can say V, that is the volumetric flow rate, that also will change, that will increase gradually. So, then this is the pressure ratio, this is the fractional volume changes, this is the conversion. So, this V by V naught or F, that also along the changes of the catalyst that we can measure. So, here it will start from 1 I said. So, V by V naught means initially that was 1, that is F equal to 1. Okay. So, initially it was 1, therefore, it is started from 1, and once the catalyst weight inside of the reactor that is changed for this particular reactions volumetric flow rate. So, it would change like this. So, F equals to I said V by V naught. So, it would change like this. So, it gradually increase. So, volumetric flow rates, so that change that inside of the reactors will be like that. So, this is the outputs or the results. So, inside of the reactor, so when we are taking ethylene as a reactant and oxygens or air as a reactant, and that is giving ethylene oxide for these particular reactions, and if we solve these two equations, so then the nature of that weight of the catalyst and conversions, pressures and volume changes, fractional volume changes or volumetric flow rate changes inside of the reactor, that easily we can predict or we can easily calculate based on the data is available. So, this is the way we can solve any numerical problem. So, here's we have started with this reaction. So, similarly some other means reactions also we can conduct this type of reactor, means packed bed reactors we can consider, we can charge the catalyst weight, and then if our conversions or desired conversion is fixed, let us say we need to convert 70%, 80% conversion for that particular reactions, if it is possible or it is achievable. So, then how much amount of the catalyst that we have to charge and what would be the pressure drop or pressure changes in that condition. So, easily we can all parameters that the required to solve the differential equations, if it is available, then easily we can design a packed bed reactor for a particular reactions where pressure drop is there, and when reaction or conversion is there. So, means how with the increase of the catalyst weight the pressure it changes, that we can calculate for any other reactions also similarly. Okay. So, today is up to this. I think it is now means clear, means what is the purpose of the pressure drops, packed bed reactors and design equations or the things argon equations. So, now it is clear I think. So, today is up to this. Okay. So, next day we will start something else or different things. Okay. Thank you.